Welcome everyone. This presentation is kind of a part 2 on a digital signature scheme called BBS Plus that we presented on at IOW 30 and its application with regards to verifiable credentials technology. So on the topic for today, we're going to go through a bit of a refresher on the problem statement and the use cases. And I want to introduce a concept of BBS Plus as kind of a generalized digital signature multi-message digital signature scheme to explain some of the more advanced capabilities it has to offer. Then give a bit of a progress update on where we're at with this initiative, and then more of an advanced feature discussion. I know Kyle marketed this as a bit of a 101, but the advanced feature section I think is probably going to be a bit more like a 201 or beyond. So broadly, just as a recap, the thing that we're aiming to solve is looking for a solution for selective disclosure of things like identity claims. That's what verifiable credentials tend to contain, and the ability to essentially do selective disclosure with them. And there's a variety. This is just pointing to the fact that there is a variety of ways to solve this problem. You can do things such as just-in-time issuance models, trusted witness, or there are certain forms of cryptography that kind of afford you the same capability, which is of selective disclosure. So just as a bit of a digital signatures 101 to kind of frame up the thinking around what BBS Plus is. Traditional digital signatures look a bit like this. You have a message, and by message I mean virtually anything that you want to sign or protect its integrity of. It can be a message or a payload. You use essentially what's known as a private key, and these are a private and a public key are often associated in the form of a key pair. And you use that to produce a signature. And then obviously on verification, you need to possess the public key equivalent to that private key, the signature and the message, and you'll have a result reported of whether or not the signature is valid. And the signature validation tells you that essentially the message is untampered with, and it gives you origin authenticity in the sense that you know who produced the signature over that information. And now what BBS Plus is, in a general sense, is what we would refer to as a multi-message digital signature scheme. So essentially, instead of a single message on the input, you can have as many messages as you would like. And essentially, you assign a group of messages, again with a private key, and then you use a very similar mechanism on the verification side. At this point, it's probably not immediately obvious why you would break a message apart. For those that are more familiar with the scheme, it probably is, but essentially what this affords is the capability around selective disclosure. So in traditional digital signature schemes, this is about as complicated as it gets: sign and verify. However, with BBS Plus and this multi-message digital signature scheme, there are a couple of further operations you can do. And there's this one referred to as derived proof. What derived proof allows you to do is to take the original set of messages that you signed, and using the issuer's public key and the signature, you can essentially do what's called deriving a proof. And importantly, in that process, you can choose which messages you would like to reveal versus which you would like to keep hidden, and merely instead just prove you know all the messages, but you're electing to only reveal a subset. And so consequently, on the verified proof side, you end up with a result where the verifier who performs this operation, so this operation is often performed by someone who's in possession of all the messages, and in the context of verifiable credentials, that's usually the subject or the holder. And then on a verifier proof operation, that's usually done by the verifier. They only have it's a subset of messages that you wanted to reveal to them, the public key, which tells them who actually signed those messages originally, the proof, which is the proof of knowledge of this signature, and that these messages, the messages that are revealed, were in fact in part of the signature. And importantly, it's the proof, not the original signature, which has certain privacy guarantees associated to it. And then you get, similar to signature verification, you get the ability to tell whether or not the proof is valid or not. And you get the similar integrity guarantees around the messages. When you're using this digital signature scheme for things like identity assertions or verifiable credentials, essentially how it looks is each message corresponds to an identity claim. So you choose which ones you would like to disclose. At last Internet Identity Workshop, we introduced this initiative and we open sourced a reference implementation for Node.js environments for both the digital signature scheme, which is the lower level, and then also the layer that links it to JSON-LD linked data proofs, which is what's used in the context of verifiable credentials and makes them applicable for verifiable credential use cases. We also open sourced a draft spec for the BBS Plus linked data proof and had that sent over to the CCG as a work item. So the progress since the last IOW, we've got improved ecosystem support now. So BBS Plus is now runnable in the browser via WASM. There's a single dependency, and I'll offer some links at the end of this presentation, called BBS Signatures, which allows you to run BBS Signatures performantly in the browser, as well as in Node environments. So that single dependency actually has the ability to detect what environment you're running in. And then we've also worked on several other language wrappers. Java, Objective-C, and the team over at Trinsic have done a fantastic job of bringing a .NET version of this to reality as well, and I believe that works in Xamarin too, so thanks to them. And the team at SecureKey running Aries Framework Go have also worked on an independent Go implementation, which is really awesome to see. So as well as that, the spec for BBS Plus signature schemes underway. So the low level sort of digital signature scheme and describing the maths and how we apply it. The definition for the key representation. So how do the public and private keys look in standardized key representation structures such as JDB key and linked data key pairs. We've demonstrated how you can integrate BLS 12381 as the curve used in BBS signatures, how that can actually integrate with DIDs. And we've showed how that signature scheme is working with DIDs in a pluggable manner. So how it's really, really easy to kind of use BBS Plus signatures with DIDs without them across methods. Then we've also worked on and done a lot of the significant work towards the more advanced features that we'll talk a little bit more about later in this presentation. So with that, I'm just going to do a really quick demo for some people that may not have seen this sort of stuff around how the signature scheme works. What I'm going to do is use a little CLI to create a DID.
Can you make it a little bit bigger, Tobias, if possible?
Yeah. How's that?
Yeah, much better.
Okay, great. So we're going to create a DID of method type key. And then we're going to specify the key type because DID key can start with different key types. ED25519 is the default, which is a different curve. We're going to create one with BLS 12381 G2. And what you'll see there is that creates a BLS 12381 DID key. So you can see here that this is a BLS 12381 G2 public key, which is capable of doing BBS Plus digital signatures. And now what I'll do is show you my input. So this here is an example credential. To many familiar with the citizen vocab will recognize this as a permanent residency card. Unsigned, so it's not a verifiable credential yet. It's a credential, but it's not verifiable. So now what I'm going to do is I am going to call issue. So this is issue a verifiable credential with a DID key, calling in the prc.json and echoing it out into a signed file. Note this takes a second, not because the digital signature scheme is slow, it is resolving the remote context. I'm not caching these contexts at the moment, and that's why it takes a second. You can run the benchmarks on the crypto operations to see just how performant it is. So now I will show the signed result. As you can see here, this is now a verifiable credential. It's got a proof on it. It was signed by that DID key. And it is now verifiable. And so what I can do is verify it. And you can see that that is verified. That's just using the did key method, but as you can kind of see, you can use a variety of different did methods with it. Now what I'm going to demonstrate is what we call the frame. So this here is what's called a JSON-LD frame. This describes if you would like to do a selective disclosure request on this credential, what you would like to reveal from it. So this syntax is from the JSON-LD frame API, which is a web standard W3C. And this is essentially saying I would just like my given name, family name, and gender from this credential. So now what I'm going to do is call derive, and that's the derive proof operation that I showed earlier on with the diagrams, calling in the frame, calling in the signed credential, which is this here, and outputting it to a derived file. And again, because of the cached context, that's why it takes a second. Now, if I cat that out, you'll see that I only have 3 statements revealed and a proof, which is different to the actual signature. So this is a signature, and this here is a proof of signature. And accordingly, that is what it's doing. You'll also see that there's a nonce in here that protects against replay attacks in deriving this proof as well. And then finally, you'll see that if I attempt to verify that, it will verify just like any other verifiable credential. Okay, great. So I'm just going to flip back to the presentation. So now things will probably go up a few levels in terms of complexity in terms of the conversation. So apologies for those who thought this was a 101 presentation. So a couple of the advanced features I'd like to talk about today. One is, as Will pointed out, a more privacy preserving subject authentication mechanism, more accustomed to how CL Signatures supports that today. And another feature we'd like to talk about, which is called a domain proof. So the problem is that in certain applications of verifiable credentials, having a strong identifier for the credential subject as the means of subject authentication, and that being a global identifier, unique identifier, the nuance there is important. In some use cases, it's problematic for the application of verifiable credentials from the perspective of user privacy. And so for variations where we do that, and the reason I introduced the diagrams before, we propose the kind of generalized mechanism of what we call a bound multi-message digital signature. And so whenever a digital signature, because digital signatures in general can be used to assert a variety of things, when they are used to assert claims about a subject, and I'm using the term subject in the most general capacity here, and that subject would like to authenticate as the subject of those claims, we can produce digital signatures that actually bind some key material from that subject into the signature, such that when they want to derive proofs, presenting a subset of those claims, they must be in possession of the associated private key in order to do so. So in a general perspective, the sign and verify operations end up with one extra argument, which is the subject's public key. And then on derived proof, you'll note that there's one other argument that is present here. And this derived proof requires the subject's private key because you essentially have to have knowledge of all of the messages that were signed. You have the issuer's public key because you're proving that this information was signed by the issuer. You have to have the signature you want to prove from, and you can essentially create a proof. And if you chose to, say, reveal only 4 of the 5 messages here, then the only things you need on verification is the issuer's public key, these, and the proof's valid. And because at the signature level, you'll know signature level because of the presence of what's called a generator value, that there was a public key involved in the original signature and the proof, and you are proving knowledge of that private key without revealing the private key or the public key. So all you know as a verifier is that there was an unresolved key pair bound into this that you don't get the ability to know. So you get subject authentication without a strong identifier for the subject. The solution, the way that it ends up looking, for those that were looking before, this is what a BBS signature with did-based subject authentication would look like. down here, this here instead. And importantly, this isn't actually signed by the issuer. It's an indicative field that's just referencing the public key that the signature was bound to. So it's really just a hint, because this is only for the subject. The subject never reveals this to a verifier directly, or shouldn't, because they should be deriving proofs off it. But essentially they would receive this, and then this tells them which key they need to dig out of their KMS in order to do the derived proof operation. That's what it concretely translates to. And then when you do a bound signature proof, so this is a different type, this is what we call bound. You notice there's no globally unique identifier in here, but a byproduct of verifying this type of proof, you know that both the issuer has originally signed and presented the information, and the subject, a part of creating this proof is predicated on the fact that the subject had the private key, that the original signature the proof was derived from to create this proof. They possessed that. And so this is what it would look like in a verifiable credential presentation. Note there is no subject authentication proof out here for those who are really familiar with VCs. So with this, there is kind of a new problem. How does a verifier know whether or not the exact credential they've seen before, or the credential subject described by the credential, they've seen it before? And essentially there's a need to have a domain or verifier specific proof that remains consistent over repeat presentations of the same credential or credentials from the same subject. So that's the kind of problem. So essentially we need this, this concept of a domain or a verifier specific proof for the credential subject that stays consistent on repeat presentations of the same credential. So essentially what's needed is, when you actually sign the information, is you need a sort of a separate attribute, and we propose that that could essentially be the subject ID. So in most identity systems today, there's a way in which you describe the subject. It's often a GUID, it's an unauthenticatable identifier that systems have to identify users in their systems. And we would say that that would be a good candidate as the value to go in here. And essentially that's a value that the value would never be revealed in any derived proofs, but it would be bound into the signature as essentially one of the messages, but in a slightly special way. And what that allows us to do then is, when we are deriving a proof, we can take the domain. And what I mean by the domain is, from the JSON-LD proof perspective, there's a field called domain, which is the domain the proof is intended for. So that's usually the identifier for the relying parties. Like it might be their DID, or it might be a URL identifying them at a web origin. And I'll give an example of that in a second. And essentially what you can do is, you can, based on this value, you can create a domain specific proof. And the benefit that is if you rotated the key pair, if you reissued a new credential and you wanted to rotate the subject key pair for good cryptographic hygiene, as long as this value stays consistent, you can have a new credential issued, but you can the domain proof will still remain valid. So it removes the ability for essentially Sybil attacks with verifiable credentials in ZKP schemes. And again, the vulnerability that Daniel Harmon and others spoke about really elegantly in the RWAT paper. And then essentially on verification, if you possess the domain that the proof was essentially created for, you can get that validation. And so that is essentially the high level concept of the domain proof. And so how it kind of ends up looking in a bound signature proof is, this field will be familiar to many already in the VC space, which is the domain. And then this is essentially a proof. And essentially you have to prove a couple of things. You have to prove that the domain specific value you're getting off the subject ID and produce that. And then you also have to prove that the value that was used to create this proof is actually a part of the signature. And that's loosely, essentially, or high level, how the concept is designed to work and how it will manifest. And we believe with that mechanism, you have the ability to have a presentation where you can detect repeat presentation correlation of the same credential, and therefore you adjust that kind of incentives around the link secret and exposing verifiers. So if a credential was put on the black market and it was represented to the same verifier, to the same domain, you would be able to detect reusage of that same credential.